see how it works. Sometimes it works, sometimes it doesn't. But let me do this. This, and then oh, that's not what I wanted. All right. Okay. Okay. When the light bulb burns out in a series circle, what happens to the other bulbs? They go out. Yeah, they go out. That's easy, right? Simple. Okay. Oh dear. Angle. All right. Second one. Second one. Stop. Don't do that. What kind of interference occurs when these two pulses meet? You have two choices: constructive or destructive. Do they build each other up or knock each other down? They build each other up. Which one builds each other up? Constructive. Yeah, constructive. Right. Okay, so those are daily two. All right. Questions, comments about that? All right, awesome. Ben, would you please get out something to write with, something to write on? We're going to take some notes today. Okay. We'll do a lot of writing early, and then not much writing later on. Just a word of warning on that. So I'm going to be working from a PowerPoint presentation that I have. Played from the start. All right. On magnetism. Okay. Magnetism. All right. Where's the word magnet come from? Remember, that was one of the 20 questions. Sorry? Magnesium? For what country? Yeah, it was Greece. Okay. According to my research, and yours may have differed a little bit. According to my research, it comes from Magnesia, which is a province of Greece, you know, where they dug up these naturally occurring. They dug these rocks out of the ground that had these like magical properties. You know, they would touch the rocks to, you know, these rocks were amazing. But I don't have one yet. I've got to order one. But they were amazed that these rocks would, like, if they touch it, you know, if they touched it to a paperclip, you know, it would pick up the paperclip, you know, like magic, right? Yeah. Actually, I was kidding about that. They didn't have paper clips 2,000 years ago, but they did have these magical rocks that exhibited these magical properties. And they actually gave this mineral a name. They call it magnetite. I'll never test you on this stuff. You don't have to write this down if you don't want. And it's a mineral that's naturally magnetic. Okay. And they ended up, the Chinese, they placed these rocks on leaves, and they put the leaves in water. And these things would always rotate and orient themselves the same way. They were the first navigational compasses, and so they could take them on ships, and they could go out of sight of land on a cloudy night, and they still could orient themselves. They still could know where they were going. They were the first navigational compasses. A couple thousand years ago, the Chinese invented them. All right, so they ended up calling these lodestones or leading stones. All right. Way before they knew what magnets actually were or how it worked or anything like that, they just saw what it did. You know, they took advantage of it. All right. Substance that exhibits strong magnetic properties is called ferromagnetic. Ferromagnetic. Ferro. What does that refer to? Chemistry students. Ferro? Oh, not that kind of ferro. not the pH kind. The FERRO kind. What does that refer to? Chemistry students? What is Fe, the chemical symbol of? Iron. Yeah, ferrum is the Latin name for iron. And so this came to be called ferromagnetic because it had to do with iron. Okay, that's where the word comes from, iron. Okay, now there are three elements in the periodic table that exhibit ferromagnetic properties: iron, nickel, and cobalt. Okay, and they're really easy to remember because they're right next to each other on the periodic table. All right, iron, cobalt, and nickel. All right, these are the three elements that exhibit ferromagnetic properties. All right, now you also may have heard of neodymium magnets. Okay, neodymium magnets are really strong magnets. And neodymium is actually a rare earth element. But a neodymium magnet is not magnetic because of the neodymium. A neodymium fundamental particle has this, notice 14 iron atoms. Okay, and it's the 14 iron atoms that are doing all the work as far as that goes. I'll never test you on this stuff. I'll never test you. You don't have to write it down if you don't want to. By the way, this presentation is loaded on Schoology. So you could literally go out and print it out. You wouldn't have to take any notes at all, or very few anyway. All right, so neodymium magnets, and I don't have any. There weren't any when I started this job, and I haven't bought any yet, so I can't show these to you. I got to buy some of these. You can get them on Amazon for cheap. I don't have them yet, but neodymium magnets are really strong magnets. Okay, hard drives. If you have a computer that's dead, don't just chuck it away. Take it apart and get the hard drive. And neodymium magnets are hard drive magnets, and they're really strong. Okay. The next time my computer dies, I'm going to take it apart. I should have done this. Well, I left the neodymium magnets back in my old job. But the next computer that crashes and stuff, I'm going to take it apart and get the neodymium magnet out of the hard drive. They're really strong. Okay, and they're super useful. Okay. There are other types of substances that exhibit other magnetic properties. You may have seen it in your research: paramagnetic and diamagnetic. I'm not going to go over those. I'm not going to take the time, but they also exhibit some weak either attraction or repulsion. Okay, I'm not going to cover that, but if you see it in your research, that's what they do. Okay, where does magnetism come from? This is a big mystery for a long time, and they didn't figure it out until about 100 years ago. All right, turns out that magnetism comes from the motion of electrons. Okay, the orbital motion of electrons around a nucleus. Okay, and these electrons, they orbit and they produce what's called a magnetic moment. And so an orbiting electron will produce a magnetic field. All right. However, when electrons orbit an atom, some are doing this, and 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 their orbits are random. Okay. So their magnetic properties tend to cancel each other out, right? Actually, most of the magnetism comes from electron spin, because electrons spin, okay, about an axis. All right, and it's the spin of electrons that produce most of the magnetism. Now, we use this globe to represent an electron. Right now, there's two ways an electron can spin. It can either spin that way or that way. Okay, and it can either spin clockwise or counterclockwise when looked down from above. And if it spins that way, it produces we call this spin up, because if you take your right hand, your thumb points up. If you take it down, spin down. So electrons can either spin up or spin down. Okay, well, if you remember your chemistry, how do electrons fill orbitals? How many electrons can fit in any one orbital? And the answer is 2. Well, the reason remember that, chemistry students? Okay, and the reason for that is one of those electrons has spin up and the other one has spin down. Okay. Yeah, the S orbital has only 2, then the P's and the D's and stuff like that. But within any suborbital, there's spin up and spin down, 2. And there's a reason for that, called the Fermi exclusion principle, but never mind about that. So one has spin up and one has spin down. Well, those magnetic properties will also cancel each other out, because one magnetic field is going to cancel out the other one. Okay. Oh, so each electron is itself. Each electron is a magnet. But as they fit in orbitals, they tend to cancel each other out. Okay, in most atoms. All right. Okay. Except for iron. Okay. Iron. Iron is special. And I don't know why it does this. And I don't know if anybody knows why. It just is. Iron is special. Actually, iron is special for a couple of reasons. But iron is a very special thing. All right. I'll let you write that stuff down. In most atoms, the spin of electrons cancel each other out. All right, except for iron. Iron has 4 electrons in the d orbitals that don't cancel out. They all spin in the same direction. Why? Nobody knows. At least I don't. It's just energetically favorable that they do. So in iron, they have 4 electrons whose spins do not cancel out. Okay? And this is what gives iron the ferromagnetic properties that it has. Iron is special. Okay? It's the 4 unpaired electrons. Okay. Now there's a question so far. Am I going too fast? Am I going too fast? No. Sorry. From your lab, what force exists between like poles? Like North Pole and North Pole. Repulsion. What force exists between unlike poles? Attraction. You guys knew that coming in, right? You like learned that in 4th grade or something like that, right? So we know that, right? Like poles repel. I'm sorry. Oh, okay. Yeah, okay. Like poles repel, opposite poles attract, right? When have we heard that before? When did we hear something like that before? Oh yeah, the electric force. Okay. All right. Let's say I take this bar magnet and I'm the Incredible Hulk and I snap it in 2. What do you have? What would I have? A broken magnet, right? No. What would I have? 2 magnets. Yeah. Let's say I took one of those and snapped it in half. Took that, snapped it in half. Took that, snapped it in half. I'd have a whole bunch of magnets, right? I could take it down to the individual atoms. Hey, I could take it down to the individual electrons. And I have a whole bunch of magnets. Moral of the story. Magnetic poles cannot be separated. Okay? Can I separate charges? Can I separate a positive and negative charge? Sure I can. Just comb my hair. It's easy to separate charges. It's not only difficult, it's impossible to separate magnetic poles. Okay? All right? It's not only difficult, it's impossible. The magnetic force is also a non-contact force. So it has this notion of a field. Somehow this magnet can affect the space around it so that if there's a ferromagnetic material in that space, then it is affected. Okay. Where have we heard that kind of stuff before? So Faraday's concept of a field was expanded to magnetism, okay, to explain non-contact forces. Okay. Get your labs out, please, and go to page 2. Get your labs out. Go here. Okay. What you did, well, actually, what I did was I had a bar magnet. Actually, I got to move this. You can move it down here. In part 2, we had a bar magnet and we sprinkled iron filings and it formed kind of arcs like this. Yes? Yes? Okay. All right, would you please put an N, I left it blank intentionally, put an N on the left side and an S on the right side, indicating a north and south pole. Okay, now to map the field around the bar magnet, how did we map an electric field? We used a very, very small positive charge. We pushed it down, we let it go, and we saw where it went. To map a magnetic field, we do something similar, but we use an independent north pole. Wait a second, Stars. You can't have an independent north pole. You just told us that they can't be separated. Yeah, I know that. But let's just pretend you could. If I put a north pole right here, where would it go? And let it go. where would it go? It would go here and then here, right? Okay, so that means that the magnetic field lines do this. Please put arrowheads on each and every line. Magnetic field lines go from north to south. Okay, so to map this, we use an independent north pole. Okay, and we draw arrowheads on the lines from north to south. Okay, excuse me for just a moment. I got to check on something. I wonder if people have been waiting in the waiting room. Nope, they're not. Okay. 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 All right. So come on back. Here we go. So I get that. So we use an independent north pole. The field lines begin on the north pole and end on the south pole. Okay. Where is the field the strongest? Where's the field and here the strongest? On the ends? Yeah. Yeah, check it out. There's paper clips here. You know what I'm gonna do? So that people can at home see. So hopefully you can see. Strongest at the poles, right? Go towards the middle. Oh, yeah, I can hold up one. Hold up two. Okay. Hold up two. Can I hold up a whole bunch? No. So the field is strongest at the poles. Okay. Field is strongest at the poles. Now, check this out. You can't see this at the line. But now, listen to this. Keep drawing lines. Keep drawing lines. Keep drawing lines. Keep drawing lines. There's always a hole right there. You know what that means? That means that there's no field in the middle. There's no field in the middle. Okay? There's no field in the middle. All right. So this bar magnet in the middle cannot hold up a single paper clip. Not a single one. Okay? Not a single one. There's no field in the middle. All right? All right. That was kind of fun. Now, let's this thing up. A horseshoe magnet. Okay? A horseshoe magnet is stronger than a bar magnet. Why? Because the poles are closer together. She rings the bell. Because the poles are closer together. So therefore, a horseshoe magnet is strong. But there is no field in the middle. No field in the middle. Go ahead, Steve. It would just go here. Yeah, there's nothing over. It might wrap around here.
Yeah.
Yeah, it probably does. Okay. Yeah, but it's really strong here. It just gets weaker. But right there, no. 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 Yeah. All right. That was kind of fun. Clean up here, messy. Now, stuff's out. This bad boy. This is really strong horseshoe magnet. Okay. Man. strong, okay? But no force in the middle. Now these, let me get this, I get this out. Yeah. These really have the ball there. Pick them right off the table, right? No force in the middle. No field in the middle. Oh. I see. Now here. There. But it's really weak. Yeah. I caught it even without my eyes on. How about that? It's here, but it's weak. See? Yeah, man, that's a good fun. But I don't want to lose these. So. Yeah. Yeah. Okay. Maybe you get a chance to play with this later on. Okay. Next. Refrigerator magnets. They're only magnetic on one side. Why? Because of the paper, right? No. Magnets can act through things. For example, magnets here. They can act through things. Actually, if I had some neodymium, I could have one on each side of my hand. Oh, no, it doesn't hurt at all. If you get some neodymiums, you can do that.
Will any amount of magnetic force alter like an iron in your blood?
Maybe. I don't know. Maybe. Okay. Now we take advantage of this. Anybody have a treadmill? Ever been on a treadmill? You know the little button that you put on to make the console work? Magnetic switch. That little thing is a magnet. And underneath the console, there's a couple of wires that are separated a little bit. And there's a ferromagnetic thing, steel right underneath it. When you put the button on, it picks up that little thing, connecting the wires. Circuit flows. Okay, turning on the console. When you take it off, cuts away, opening the circuit, console goes off. Simple, right? Magnetic switch. Okay, simple. Like that. So magnetism can act through things. So it can act through the paper. Why is it only magnetic? Why is it only magnetic on one side? Because horseshoe refrigerator magnets are a bunch of little horseshoes. They actually call them feet. If it was strong enough, would it stick to the board? Yeah. Would it stick to the board? No. So there's a bunch of little horseshoe magnet stuff on this thing. Sprinkle some iron filings on here. And you'll see them line up in rows.
There's a little end sticking out. from the horseshoe magnet.
Yeah, the poles are on the poles are on this side, the middle's on that side. Yeah. Yeah. Mm-hmm. Yeah. It's attraction between, there's a steel backing for this. And that's why they stick. Okay. Or they're attracted. All right. So refrigerator magnets. All this stuff that you may or may not have known. Okay. What's next? Oh yeah. One of these things. What's this called? Anybody know? I wouldn't think so because you're city folks. This is a cow magnet. All right. What's a cow magnet used for? To attract cows? No. No, it actually can keep them alive. You know, where I used to teach, there are kids on the farm, and then say, oh yeah, that's a cow magnet. You know, what's it for? Well, if a cow's grazing in the field and it swallows a nail or some piece of wire that's in the grass or something, and it went through its stomach. How many stomachs does a cow have? 4. And if it went through the 4 stomachs and the intestines, you can just rip it up, kill the cow. If a farmer suspects that this may have happened because the cow's acting like it's sick or something, if it suspects that it swallowed something like that, it'll take one of these cow magnets and shove it down its throat. Okay, they actually have a little gun to do that. Okay? And it sits in the first stomach, and it will collect any metal that might be in there, and it'll prevent it from going through the intestinal tract. Okay, and it just sits there. Yeah. Does a cow poop it out? No, it just sits there for the rest of its life. I imagine that slaughterhouses find these things routinely, regularly. And these things are cheap. I picked up a 3-pack. Of course, it was a long time ago, probably before you. 3-pack are like $5 at a store. So they're cheap and strong. Okay, so cow magnets come up on Amazon for cheap. They're cheap and they're strong, but they can keep a cow alive. Okay, so all these applications for magnets. Okay. All right. What else? All right. Getting back to your lab, we had a case where you had this is one thing you did. You had lines. Oops. You had lines that did this. Okay. Let's draw some arrowheads now. Away from the North Pole, yes? Then we had lines. This. Then we had lines that did around around unlike poles that did this. Okay. Also, let's draw some arrowheads now. Okay. All right. So the field contained like poles and unlike poles. All right. All right. Oops. You know what? This bad boy is affecting this suspended bar magnet. I don't want to. All right, now. So I get that, did that, did that. Oh yeah. Okay. Let's say bring this meter stick near my suspended magnet. When I do that, does anything happen? No. Just kind of doesn't do anything. Okay. What happens if I bring a magnet nearby? Is it affected now? Yeah. So I can affect a magnet without touching it, not with a meter stick, but with another magnet. So only a magnet can affect another magnet without touching it. Okay. If I orient this and I let it go, it rotates. And it always ends up in the same place. Why? What causes it to move? Earth. Yeah. Well, if only a magnet can affect a magnet without touching it, and Earth can affect a magnet without touching it, what does that tell you about Earth? Earth is a magnet. Yeah. Earth is a magnet. Right? Okay. So Earth is a magnet. All right. that begs the question, where's this magnetic field come from? Now, 300-400 years ago, they were wondering about this. They didn't know a whole lot about the Earth. They thought initially that up in the North Pole, where Santa Claus lives, there was this gigantic mountain range of lodestones. And that gigantic mountain range affects magnets everywhere in the world. But then they went up there and they found out there's not a gigantic mountain range up there. What's up there? Ice. It's an ocean. That wasn't it. So they said, okay, let's say you just cut Earth open like an apple. If we did, you'd find a giant bar magnet inside, right? And that's what caused it. But then they learn more about the Earth and they say, well, if you start digging a hole, it's not solid all the way through, right? It's going to end up being liquid in there. So that wasn't it either. So about a little more than 100 years ago, they figured out that it wasn't because of this stuff. It was because of the liquid iron in the Earth. You know, when Earth, in its very early days, Earth was just a giant liquid ball because it was so hot. It was just a ball of lava or hot stuff, you know, and the heavy stuff like iron sunk to the bottom. Lighter stuff came on top. Well, iron sunk to the bottom. And it's so hot that it's still liquid. And it's moving. It's moving. Okay. And now we know that Earth's magnetic field is created by currents in the liquid outer core of Earth. Earth, the layers of Earth. Outside it has a crust, and then it's liquid, and then at the very center it's solid. Now, what's interesting about this is that an egg, you know, an egg has a shell, it has egg white, it has an egg yolk. The proportions of thickness of an egg shell to its white to its yolk are very similar to the proportions of the crust to the liquid outer core to the solid center. The crust of Earth is very thin, it's only about 50 miles thick. An eggshell is really thin also. And the proportions are equal. So, you know, God could take Earth and crack it on the side of a glass, you know? The proportions are similar. And it's the you know, moving iron is really hot, right? And so the currents in there are generating Earth's magnetic field. Okay. All right. Okay. Now, lab number one, observation number one. Which pole of the bar magnet, suspended bar magnet, pointing toward north, where Santa Claus lives? The north pole of the magnet. Okay. So what does that imply about the polarity of Earth's north pole? Is it a magnetic north or a magnetic south? It's a magnetic south. Why? Because it's attracted to the north. Well, there's doubts. Why did they call it a north pole then? Well, because that's before they ever knew any of this stuff. They found that this end of this thing pointed to the directional north, so we'll call that north. You know, later on, they figured out, oh, it's not really, but that's okay. They left. Okay. But that's not even the weird part. The weird part, it gets stranger than this because the magnetic pole and the geographic pole are not in the same place. At the time that I wrote this, going on 20 years ago now, it was in northern Canada. It's not there now, though. According to your research, where is it? Yeah, Siberia. Okay, so it moves. You know why? Why does it move? I don't know. I don't know if anybody knows. Probably just because of anomalies in the currents. You know, all right? It moves around. So what that means is, if you're going to travel to the geographic North Pole, the place where if there was a stick through the Earth and it spun about the stick, you know, your compass would not point to this place. It would point to a different place. All right. Okay. But that's not even. I'll never test you on this stuff. By the way, this is just fun. Okay. That's not even. So there's what we call magnetic declination, and that's the difference where the compass is to where true north is. Okay. And where I used to live, right here, the geographic pole and the magnetic pole were very nearly lined up. So the compass did the compass needle pointed very close to where true north was. That is geographic north. But now I live here. And it's a lot different. Check this out. As far as I can tell, the edge of my lab table points true north-south, true north-south. Okay? Look how far this is off. This is pointing this way. There's a lot more than I thought it would be. Right? I was surprised that it was this much, the magnetic declination, where we are right now. Yeah. All right. Okay. Something else. And again, I'll never test you on this stuff. Magnetic inclination. The field lines of Earth, the field lines of the magnetic field only are parallel to the surface at the equator. Everywhere else, they angle in or out. You can measure this with a special compass called a dip compass, which I don't have here yet. Okay, magnetic inclination. Oh, by the way, I forgot to mention this. Here are the magnetic field lines of Earth. Remember how they go from north to south? Remember that? So the field lines of Earth start at Antarctica and they end in the Arctic. The way I remember this, penguins live in the South Pole, polar bears live at the North Pole, so they don't live in the same place. I've had to say, wait a second, don't polar bears hunt penguins? No, only they're in a zoo. They live in different places. So the field lines go from penguins to polar bears. Penguins to polar bears. That's the field lines of Earth. Okay? Forgot to mention that. All right, anyway, magnetic declination, magnetic inclination. So the pole moves around, You got to pay attention to that. Columbus actually knew that they were off when he came over from when he sailed to the New World. And he had to kind of account for it a little bit. But that's not even the weird part. Here's the pole shift. Notice, got a lot larger the last couple decades. That's not even the weirdest part. Weirdest part, it appears as if the poles reverse polarity every 200,000 years or so. What does that mean? Well, that means that if it happened, I'd come to work tomorrow, and this suspended magnet would be pointing the other way. Okay. Now, actually, they don't know how long it takes. It says it might take as long as 20,000 years for it to actually flip, but it has flipped polarity in the past. Now, I know what you're thinking. You're saying, how the heck did they know that? Well, they know because of the Mid-Atlantic Ridge. Okay? Now, before I talk about that, let's talk about volcanoes. Volcanoes erupt lava, liquid iron. And so picture a volcano erupting. The lava comes down the hillside, finds a level area, and pools there. But while it's still liquid, all those little iron atoms in the liquid lava all rotate because they can. Earth's magnetic field affects them. And they all rotate, and then they cool and solidify. And so if you look at lava, dried lava, microscopically, all the iron atoms will be pointed in a single direction, north. Okay, well, the Mid-Atlantic Ridge, lava is coming out of this Mid-Atlantic Ridge, and it's pushing America and Europe apart about this far every year. Okay, and so lava comes out of there, they rotate and solidify. And then they go a little bit farther away from the ridge to find older rock. It's the other way. A little farther away, it's the other way. So reverse polarity. That's the evidence. Okay. Now, we're actually overdue for a shift. We're overdue. Okay. Why does that happen? Nobody knows. How long does it take? Nobody knows. The next time it happens, we'll study it like crazy. But until then, we don't know. Now, what's going to happen? How's that going to affect us? When that happens, how many stars are there going to be like major earthquakes and tsunami and stuff like that? No, probably not. Probably not. It's not going to affect this animal, but it will affect some. What animals? Birds. Why? Because they, there's a word for that. Starts with an M. Yeah, they migrate. So birds migrate. What else? What other animals migrate? Whales, monarch butterflies, lots of animals migrate, and they follow Earth's magnetic field to do that. They have little compasses in their head. They actually did an experiment. Passenger pigeons, you know, the ones that know where to fly. I think they did this in Britain. They took a passenger pigeon, they took a bunch of passenger pigeons, and they put magnetic hats on. And they didn't know where to go.
I'm sure like they have to do their eyes or something like that, where they cover it,
Really? Okay. Yeah. Yeah. The magnetism messed them up. And then they took the hats off and they knew where to go. Okay. So I think it would affect them, at least for a while. All right. I'm sorry.
Like would all the compasses
Yeah. Suddenly, it might take a number of years, but yeah, they would eventually be reversed. Yeah. Yeah. The one that used to point north, but now points south. Would it freak everybody out? Probably not. Yeah, you'd adjust to it. Even without GPS, you'd adjust to it.
all in different
I don't know. I don't know. We'll have to wait till it happens and then find out. Yeah, I don't know. Will geographic north and magnetic north be the same? Not in the same place necessarily, but at least near each other. Yeah. Maybe by coincidence they'll be in the same place for a short time. Yeah. So when it happens, we'll okay. So cool things about the Earth. Next, domain theory. I want to get through. Let's see. Yeah, okay. I'll get through this, and then I'll let you. We'll call it a day. Domain theory. Okay, now so we said each iron atom is a magnet, and these atoms will cluster in regions that we call domains. Okay, I'll let you write that down. Then I have a little thing for you. Okay, put your pencils down. Do this. Make a box with your fingers. Is there a little airspace between your fingers? Yeah? How big is it? Pretty small, right? That airspace is the size of a domain. It's a box or a region about 1 millimeter on a side. And a millimeter, if you have a mechanical pencil, a millimeter is the diameter of the lead in your mechanical pencil. So that's how big a domain is. Okay. Now atoms are really small. So each domain contains millions of atoms, right? But they will within a domain, the magnetic fields of the atom will line up. Or sorry, the magnetic fields of all the iron atoms will line up. And I drew this. No way should you draw this. Okay, but within the domain, all the iron atoms might point this way. Within this domain, it might point that way. Within this domain, it might point into the board. With this, in this domain, it might come out of the board. It's just they're all random. In an unmagnetized ferromagnetic material, the domains are randomly oriented. Okay, the domains are randomly oriented. All right, and that's why when you try to pick up a paperclip, now. When you try to pick up a paperclip with a nail, when you try to pick up a paperclip with a nail, it didn't work because the domains in the nail are all randomly oriented. Okay, but when I attached the head of the nail to the North Pole of the magnet, now it did pick them up. So what did the magnet do to the domains in the nail? Yeah, it ordered them. It lined them up. Yeah, before they were random, okay? But when I touched it to the nail, this caused the domains in the nail to line up. This is called induced magnetism. I induced the nail to become a magnet, okay? And we actually did that, well, so I'll delete that, in our lab. Actually. In our lab, you had a nail between the North and the South Pole, and hopefully what you saw here were lines going from the magnet to the nail, because the magnetic field, the magnets induced the nail to become a magnet, okay, by lining up the domains. Oh, by the way, what polarity does the head of the nail have in this particular case? You have two choices, north or south. South, yeah. But I drew them in dashed lines because, yeah, it can pick up the, pick up the paper clip now. Oh, sorry. Those of you at home. We just drew this. Sorry, I forgot to orient it. That, but this is only temporary, because when I take it away, what happened when I took the magnet off? What happened to the domains in the nail again? Yeah, they became random. Yeah. Okay, they became random. So initially, they're randomly oriented. The nail lined them up, or the magnet lined them up. This is induced magnetism, but it's temporary. When I remove the magnet, when I remove the inducement, the domains randomize again. Okay, because when they're random, the one domain's like this, one domain's like this. If I force them to line up, I'm kind of like stretching some springs. I'll get out of your way. I'm stretching some springs. When I take the force away, they go back to where they were. If I want them to line up permanently, I have to break those bonds and form new ones. And that creates energy, or that requires energy. So this nail won't become a magnet all by itself. I have to break the random domains and to force them to line up. Okay, and I can do that. Okay? But it requires energy. Now, if I leave these bar magnets like for a long time, they lose their magnetism. They lose their magnetic properties, because within like the bar magnets that you guys use, all the domains they're all lined up like this. Okay. North pole, North pole, North pole. What do North poles do to North poles? They repel them. So yeah, these are like this now, but if you give them energy, or you wait long enough, it will find energy from somewhere, and it will randomize. So what that means is bar magnets will lose their magnetic properties over time. Okay. Now, how can I make it happen? Well, I can make it happen by doing stuff like this, dropping them a bunch of times. Dropping them. This is going to be loud. Sorry. Okay. Just drop them a bunch of times. That can give you the energy to randomize the domains to the point where they're not magnetic anymore. Okay. If you drop them, if you heat them, if you hit them with a hammer, or if I just put them in my cabinet and wait a year, when I dig these out of here next year, they're going to be like this. Okay. Well, how do I remagnetize them? How do I get them? How do I remagnetize them? Well, I use a magnetizer. This requires energy, so I got to plug it in. Turn it on. All right now. Nothing. North pull down. South pull down. Rigid. Push a button. Done. And now they're magnetizing. Okay. So every year I have to do this. Got to remagnetize the bar magnets because they will lose it over time. Okay. It's really handy to have a magnetic screwdriver because if you have screws that are really small and have to go into a really tight place, it's really nice for a screwdriver to be magnetic. The screwdriver is not magnetic. How can I make it magnetic? Put it in here. No. Rigid. Push the button. Doesn't that work? Work. Okay. It's really handy to have a magnetic screwdriver. So, bring in a screwdriver, we'll magnetize it for you. We'll have a magnetizing party. All right? Because it's really handy. When you need it. Right? So, you know, magnetic screwdriver. Go ahead. No, it doesn't matter which one I put it in. I mean, what polarity does that have? I don't know. Yeah, what pole is that? What letter? This is north. So it turns out the screwdriver, that's a north. It would still pick up the paperclip if it was a south, though, right? Still pick up paperclip. Okay. So it doesn't really matter. I don't know. We'll find out together. Okay. Ask me at the end of the year. We'll see if it's still magnetic.
Does the bridge just kind of?
Yeah, it connects it. Yeah. Yeah. Go ahead. Yeah, if I wanted to. Yeah. Do I want to? Not really. I'm sorry. I'm sorry. No, I don't believe so. Let's see. Okay. So N repels N. Okay, let's switch it. Just for fun. Are they gonna like explode? No, I don't think so. We'll find out together. Now that should attract the north. Should attract the north. I broke it. I broke it. Oh, let's fix it. Let's fix it. Otherwise, it really messed me up. Yes. And repels N again. Yeah. Okay. Okay. You can really mess somebody up, yeah. Ooh. Ooh. Okay. I gotta plan this. I gotta plan this. I gotta mark these somehow so I know which is which. You know, I can mess you guys up. Sounds like fun. No. What? Yeah. I confuse people enough. I don't want to do it. I'm gonna do it first. Okay, I'm gonna stop there. The next thing is electromagnetism. That's a whole other topic, and I only have 10. So I'm going to stop there. Would you please take the rest of the time, take a look at your lab questions. Do you still like your answers? Take a look at your 20 questions about magnetism. Do you still like your answers? Here's what I'm going to do with those 20 questions about magnetism. Eventually, and when I say eventually, I think it's going to be Wednesday for you guys. I'm going to collect it, okay? Because next class period on Tuesday, I'm going to go through. I will have gone through all the stuff that you need to do the 20 questions, and then I'm going to collect it, and then I'm going to select 4 questions at random. I don't know what they are. I'm going to select 4 questions, and to get 10 out of 10 points on this, on the 20 questions, to get 10 out of 10, you have to have all 4 correct. Okay, you get 8 points for having answers for all, and you get a half a point for each correct answer of the 4 that I picked. They're not going to be the hardest ones. They're going to be some of the easier ones. Okay, They're gonna be ones that, yeah, they should have been able to get that one if they were paying attention.
Without this,
What?
without.
No, from them. You know, yes, they should have been able to look that up and get the correct answer. Or if they were paying attention in class, they should have got that correct. It's not gonna be the harder one, all right? Ms. Thomas, which four are you gonna pick? I don't know yet. I won't know until I get it. Okay, if I did, I wouldn't tell you. Okay, so look over your answers, talk about them with each other, make sure you like them. And that'll take us to the end of the period. Okay, if you want to mess around with this fella, you can. Have some fun if you want. Why should I have all the fun? Okay, so you are free to. I don't know which polling this thing is for. Okay, yeah, those of you at home. All right. Were you able to see those demos? Were you able to see them? I hope. No response.
Yes.
Well, I hope you were. I'm going to stop recording this now, okay? But to do that, I'm going to have to end the meet. Now, yeah, okay, so, yeah, go ahead. Oh, bye. All right. Okay, yeah, you can go because I'm going to stop recording. All right, she left. All right, well.